This is our video about how intermolecular forces affect the properties of liquids, and the three that we're going to talk about are surface tension, we're going to talk about capillary action, which is also going to lead us to talk about the meniscus, and we're going to talk about viscosity. So just to remind ourselves about some properties of liquids, how we describe liquids in general, of our three states of matter, so solids, liquids, and gases, liquids are the most difficult to describe precisely because they're kind of in between a solid and a gas. If we talk about a gas, under ideal conditions, gas molecules are far apart and they're considered totally independent from one another. So gas particles do not interact with each other. And solids are pretty easy to describe because the particles that make up the solid are really in an orderly arrangement. So we call that like a lattice or a crystal, something like that. Solids tend to have very ordered structure. So we have gases that are totally disordered, and we have solids that are very ordered. Liquids are kind of in between. So liquid molecules interact with their neighbors, so like the particles in a solid, but there isn't any long-range order. So they're not as ordered as solids, but there's still some interaction. And that means that our liquids are going to have in-between properties of gases and solids. And so they're the hardest to kind of describe very precisely. So how we do describe liquids, or we say that the particles are in constant motion. So they're able to kind of move over each other, move around each other, not move as much as gases do, but definitely move more than solids do. The particles are in close contact, especially when we compare them to a gas. They're much closer together than a gas would be, maybe not quite as close as a solid would be. We say that liquids are almost incompressible. Now, for the world of 1A, 3A, 3B, we say that liquids are incompressible. That means that if you push on a liquid, it's not going to reduce its volume. That's unlike a gas. That's more like a solid. So we also say that solids are incompressible. They keep their volume even when you put them under pressure. And the reason why that's true is because there isn't a lot of empty space between the particles. So even when you push on them, there isn't much empty space that the molecules can move into to get closer to each other. They're about as close as they can be already. And then we say that liquids do not expand to fill the container. So I should really add expand there. And that's comparing it to a gas. So when we put a gas in a container, the gas spreads out and expands to fill the container. Liquids don't do that. If you pour a liquid into a beaker, it stays in the bottom of the beaker. And then because of all these things, we say that intermolecular forces are relevant. That's again comparing it to a gas. In a gas, the intermolecular forces are not relevant. They're not really important because the gas molecules are so far apart. Even if they did have intermolecular forces, they wouldn't really feel them. So it's kind of like two magnets being a room away from each other. Even though they're attracted to each other, the attraction is so small. That's more like how a gas is. In liquids, because the particles are in relatively close contact, those intermolecular forces are going to be pretty relevant. When we say intermolecular forces are relevant, what we're saying is that they affect the properties of liquids. So we're going to go through some properties of liquids like viscosity, surface tension, capillary action, and talk about how the intermolecular forces influence these properties. The first one I want to talk about is surface tension, and surface tension is a property that comes from a liquid's tendency to minimize its surface area. And that might seem like a weird way to describe it, but what we have in this first picture here, these are astronauts here, and what they have between them is they are looking at a bubble of water. So that is how water behaves when gravity is not pulling on it. And what it does is if you squirt any water into the air under no gravity, it forms a pretty close to a perfect sphere. So what it does is the molecules there are trying to get close to each other and they're trying to minimize their surface area. And the way to do that is to create a sphere. In kind of more everyday terms, we're not all astronauts here, so in more everyday terms, it's the reason why things that are very light, like paper clips, or if you ever seen like a water skeeter kind of bug that can glide across the surface of water, it's the reason why these very light things will float on top of water and not sink to the bottom. So even though their density is more than water, they're able to stay on the surface. So in order to minimize their surface area, liquids form drops that are spherical. Okay, so as long as there's no gravity. If there's gravity, we see droplets like this, okay, because gravity is pulling down on it, so there's more mass at the bottom than there is at the top. This happens because the layer of molecules on the surface behave differently than the interior. And so what I want to do there is I kind of want to talk about the molecules that would be right on the surface and the molecules that would be in the interior. Sometimes we also call the interior the bulk, because that's where most of the molecules are. Not all the molecules can be on the surface. So I want to look at the difference between those two types of molecules, surface molecules and interior molecules, and I want to talk about those cohesive forces and why they're different in those two situations. Over here, we have a picture of a surface molecule and its attractions, and so that's the surface one, and then an interior molecule and its attractions. The one that's on the interior, so I'm going to concentrate on this molecule right here, it experiences intermolecular forces, so we're talking about our maybe dipole-dipole forces, or London dispersion forces, or hydrogen bonding forces. All those are the intermolecular forces we're talking about. But if it experiences those forces, it's surrounded in all directions by other molecules. And so it's being attracted up, it's being attracted to the side, it's being attracted down, it's being attracted in every direction. And so it's equally attracted in all directions because it has molecules everywhere around it. That's different than a surface molecule, because a surface molecule is attracted side to side, because it has molecules side to side, and it's being pulled down into the solution by these, but it doesn't have anything up here to attract it. And so overall, the net force there is that it's mostly being attracted down and to the side, and so it's continually being pulled into the bulk of the solution. And that means all the ones on the surface are being pulled down. So everything that's in the surface is being pulled down. You can kind of think about it as the surface molecules all want to become part of the bulk. And so they tighten, and there's this attraction between them that we call the surface tension. Another way to define surface tension, so this attraction here, is we can also define it as the energy required to increase the surface area. So that is also the energy required to break or minimize these intermolecular forces. So if the surface tension is really high, it means that there is strong intermolecular forces. So high surface tension means strong intermolecular forces. Okay, now you can put a number on that. So if we're looking at it as the amount of energy required to increase the surface area, the amount of energy required to minimize those intermolecular forces, we would talk about it as an amount of energy per area. Okay, so the amount of energy we would need to have to put into an area, it's an area because we're talking about a surface here, so like a 2D type surface. Now, as we said, the stronger the intermolecular forces, the higher the surface tension will be. And water, that has hydrogen bonding as its strongest intermolecular force, has a really high surface tension because hydrogen bonding's a really strong intermolecular force, and so its surface tension is high. And that's why a lot of things can float on the surface of water. It's basically that the water molecules would rather be close to each other than letting something break through them. And so anything that's floating on top, like one of those little water skeeters or a paper clip or something like that, it's basically resting on the attractive forces between the molecules. Now, there are things that we can do to change the surface tension. We can't really change something's intermolecular forces. Water is always going to have hydrogen bonding, but we can influence intermolecular forces by changing the temperature. If we raise the temperature, we're raising the average kinetic energy, and that's the energy of motion. So there's increased molecular motion. If we increase the temperature, the molecules are moving relative to each other a lot more. And that makes it easier to stretch the surface. If it's easier to stretch the surface, the surface tension is going to go down. Like this. So the surface tension of cold water is much higher than the surface tension of warm water. And that's true for almost every substance. So we've talked about how intermolecular forces affect these surface molecules differently than the interior molecules. But now let's talk a little bit more about how intermolecular forces are acting on those interior molecules. That brings us to viscosity. Viscosity is something that you have experienced anytime you've taken maybe honey out of a cabinet on a cold day and it's really hard to get that honey to flow out of the container, or something like maple syrup. Things that have really high viscosity flow very slowly. So viscosity is defined as the resistance of a liquid to flow. Something that's really viscous is kind of like gooey and it flows very slowly. Things that have low viscosity pour right out of a container really easily. And when we think about flow, we're thinking about molecules tumbling over each other or molecules moving over each other. And you can kind of think about it like when molecules tumble over each other, if there's a lot of friction, it's going to slow their ability to move. So when I think of viscosity, I kind of think about the friction between molecules. And the friction between molecules would be influenced by intermolecular attraction, so those intermolecular forces. The stronger the attractive forces are between the molecules, the larger the viscosity, or the higher the viscosity is going to be. And that means that molecules that have strong intermolecular forces tend to be more viscous. But things get a little bit tricky here because viscosity is greatly influenced by the surface area of molecules. Okay, so if the molecules have a lot of surface area, there's going to be a lot more friction and a lot more viscosity. And viscosity is also influenced by temperature because temperature, again, is molecular motion, a measure of molecular motion. And if the molecules are moving more, they have a higher temperature, the viscosity is just going to be lower because that's resistance to flow. So if you're getting them to flow more, the viscosity is going to go down. So viscosity is a measure of intermolecular forces, but it is greatly influenced by temperature and surface area. And so it's not as much as a direct correlation between intermolecular forces. That means that we have to pick our examples pretty closely when we're trying to look at trends. So here, what I have some long chain carbon molecules like this. So as I'm going down here, all I'm doing is adding on one more CH group. Because these molecules are so similar, they're just long chain carbons, they all have the same intermolecular force. They are all nonpolar. And that means the only intermolecular force that's really available to them, the only one that they can exhibit, are dispersion forces. And those are the weakest of the intermolecular forces we've talked about. So if they're all made out of the same thing, they're all nonpolar, and they all have dispersion forces, the only difference between them is that each one is longer than the one before it. And that means that each one gets a higher surface area. So down here at the bottom is the biggest surface area, so kind of the longest molecule. And up here at the top is the shortest molecule, which is the lowest surface area. I'll label it like that. So here we can see the viscosity for the one with the highest surface area is the highest, and the lowest surface area has the lowest viscosity. And so you can see here the viscosity is greatly influenced by that surface area. If we think about this statement that the larger intermolecular attractions equals larger viscosity, I just want to reflect on how we were saying that water has hydrogen bonding, and hydrogen bonding is one of our strongest intermolecular forces, and that's why it has very high surface tension. But why isn't water very viscous? When I try and pour water, it pours right out of a glass. Even when it's cold, it's not very viscous. And the reason there is that water, so if I kind of draw my VSEPR version of water, when I look at it, it's kind of a small molecule. It has a relatively, or not relatively, but a very low surface area. And so if you think of water molecules as like little balls, they're able to tumble over each other pretty easily. There's not a lot of friction. There's not a lot of surface area where they would meet other molecules. It's not like these long ones that have a lot of surface area. So because the surface area of water is so low, it's not very viscous, even though it has strong intermolecular forces. So when you think about viscosity, it's true that in general, larger viscosity would mean stronger intermolecular forces, but that's only true if you're comparing two molecules that have the same surface area and you're trying to explain their viscosity difference based on intermolecular forces. So you can only say that that's true, that larger intermolecular attractions equals larger viscosity, if the two things you're comparing have about the same surface area. The last property of liquid that I want to talk about here on this video is capillary action. Capillary action is the ability of a liquid to flow up a thin tube against the influence of gravity. And you might think that that's really strange. Why would liquid flow up? But you've seen this before so many times. Anytime you've been reading a graduated cylinder and you have a liquid in that cylinder, it makes a meniscus. We always read to the bottom of the meniscus because the bottom of the meniscus for aqueous solutions is always the lowest point. But what we're talking about here is why does the water, or why does the solution crawl up the sides here? Why is there any slope there at all? So to explain this, we have to talk about two forces that are kind of working kind of together, sometimes working against each other. And those two forces are cohesive forces and adhesive forces. Cohesive forces are forces that attract molecules together. So for us, these would be our intermolecular forces. Why two molecules that are in here would be attracted to each other. Adhesive forces are the attractions between the molecules to the surface of the glass, so the surface of our graduated cylinder or the surface of any tube. So to give an example of how cohesive and adhesive forces can be working with each other or against each other, I wanted to use an example, again, of our graduated cylinder. So that's what we have here. And then we have some water. That's probably about the simplest example that we can use. Now the cohesive forces are the ones that are between water molecules. So that's one water molecule being attracted to another molecule. That's going to keep the water molecules as close together as they can be, attracting them to each other. And that's actually what would lead to surface tension. But it's only one of the forces that's happening. There's also adhesive forces. So these are the adhesive. The adhesive forces are happening between the water molecules that are in this area and anywhere close to the glass. So the adhesive forces are because of the intermolecular attractions between the polar water molecules and the polar glass molecules, the silicates that are actually a part of that glass on the surface. So the adhesive are the attractive forces between the water and the glass. Now, if these water molecules are attracted to the glass, why aren't they just crawling up the sides? Why aren't they just pulling themselves up there? Well, it has to do with the push and pull between our adhesive forces and our cohesive forces. The adhesive forces are pulling the water molecules up the side, but the cohesive forces are pulling the water molecules back down into the solution. So we can see that the adhesive forces are a little bit stronger than the cohesive forces because water does make a meniscus. If the adhesive forces are really strong compared to the cohesive forces, the meniscus is very exaggerated like this. Many more water molecules or many more molecules want to get close to the surface. But if the cohesive forces are stronger, we actually get a meniscus that looks like this. Okay, so this would be where the solution or the substance is, and it's actually like pulling itself away from the surface. That's what happens for mercury atoms. Mercury atoms, the cohesive forces, their attraction to each other is higher than their attraction to the surface. And so they kind of group together in the middle of the tube, trying to stay away from the surface of the glass. And that's why, actually, when we are reading the volume of something in a glass tube, we always say we read to the bottom of the meniscus. But honestly, what we've always been saying is we always read to the middle of the tube. The middle of the tube is the least influenced by this push and pull between cohesive and adhesive forces. So the middle of the tube is the most consistent. And that means that for a regular meniscus, we're always reading at the bottom. And for an inverted meniscus, we're always reading at the top. So we can actually see two pictures of the different kinds of meniscus here. This is our regular meniscus, and this is an inverted meniscus. That's actually mercury. And for a regular meniscus, we would be reading to the bottom. To an inverted meniscus, we would be reading at the top. In this picture, we see a bunch of different tubes that have been put into a purple liquid, just so we can kind of see the liquid there. And the difference between the tubes is how big they are. Some of them are very thin, and some of them are kind of more wide. So these are the really thin ones, and these are the wider ones, like this. Now you can see that the liquid treats the thinner ones differently than the wider ones. And the reason why this is because capillary action pulls the liquid, so polar liquids, up the surface of the glass tube, but it's also being counteracted by gravity. So the more mass that's in the tube, the harder it is for the liquid to flow up the sides. So for these really thin tubes, there isn't much mass of liquid to pull up, and it's easier for those adhesive forces to work against gravity. For these wider tubes, there's a lot more mass of liquid on the inside here. And so even though that there are the same adhesive forces, gravity is pulling this mass down more, and the adhesive forces aren't able to pull the liquid up the sides as well. So the result is that a polar liquid will actually move through a glass tube on its own because of adhesive forces quite well, but thicker tubes, the liquid doesn't flow through as well. And we can actually use this to move polar liquids. In your everyday life, one place that you might have seen this is if you've ever given blood and they stick your finger kind of on the side of your finger and they get a little blood droplet, they kind of pinch a blood droplet out there, and then they used to put a small capillary tube, so that's just a small glass tube, it's really thin, it's about that big. They put that capillary tube against the blood, and the blood, so if this is the surface of my finger and I have a little blood droplet there, as soon as they get that capillary tube close to the blood, so they just touch it like that, the blood flows into that capillary tube. It actually will suck it out of your finger. And so then they could test that the blood for your iron levels. But we use this capillary action to move small amounts of liquid through a narrow tube. So again, that only works if the tube is narrow and we're not trying to move a whole lot of mass. It wouldn't work for a very large tube. So we just talked about how intermolecular forces influence the property of liquids. We started by talking about surface tension, and we talked about how surface tension, the stronger the intermolecular forces, the stronger the surface tension is. And surface tension can also, besides intermolecular forces, be influenced by temperature. Then we talked about viscosity, and we talked about how viscosity can be a measure of intermolecular forces, but because viscosity is also influenced by surface tension and temperature, the correlation between viscosity and intermolecular forces is a little bit more complicated because these two things have such a big influence. And then we talked about capillary action and about how intermolecular forces are the cohesive forces, and that's acting against the adhesive forces that would attract the compound to the surface around it.